This lesson video won't introduce anything new, but it will give a summary of when to use the rules of the probability calculus in solving probability problems. The first thing we need to know is what probability we're calculating. So when we give a value to the probability of P, we're giving the chance or the probability that the statement P is true. So what's the chance that P is true? P can be any sentence of propositional logic. Let's start with the simple one. We'll focus on the sentence T, and we'll say that stands for some tree will grow 100 feet tall. When we write PR parentheses T, that stands for the probability that T is true. That is, the probability that some tree will grow to 100 feet tall. Probabilities must always be given as a number between 0 and 1. So whatever the probability of T is, it's some value between 0 and 1. The probability calculus gives us the rules for calculating the probabilities of 4 types of complex sentences. The first 3 sentences should be familiar from our study of deductive logic. The sentences that we're finding the probabilities of have the same meaning: disjunction, negation, conjunction. What's changing is that now we want to determine the probability that sentences of each type are true. So PR, P disjunction Q, that's the probability that the disjunction P or Q is true. PR parentheses negation P, that's the probability that the negation, not P, is true. PR P conjunction Q, that's the probability that the conjunction P and Q is true. The last thing that looks like the probability of a complex sentence is actually shorthand for a more complex probability calculation that we'll look at in a minute. But the important thing is that this symbol is unique to probability theory. So PR, P bar Q, that's the conditional probability that P is true given that Q is true. So this tells us to focus on the circumstances where P is true and then ask in what proportion of them is P also true. What rule we use in solving a probability problem depends on the nature of the sentence we're asking the probability of. So for this, we're going to have to remember some of our concepts from deductive logic. The probability of P or Q asks us what's the probability of a disjunction like P or Q. So an example of when you would use PR, P or Q is for something like, what is the probability that it snows or it rains? We see that or, that tells us we have a disjunction and we're asking for the probability of that disjunction. To determine the probability of a disjunction sentence, we have to use one of our disjunction probability rules. We can always use the generalized disjunction rule. This will work no matter what. That tells us the probability of P or Q equals the probability of P, one value, plus the probability of Q, that's another number, minus the probability of P and Q. Remember that what's distinctive about probability calculations is that sometimes the probabilities of complex sentences, if you want to get that value, you have to know the probability value for another complex sentence. In this case, you have to be given the probability of the complex sentence P and Q. But we'll also look at a rule that allows us to calculate the probability of P and Q. And sometimes what rule you're able to use depends on what values you're given. But what rule you have to use will always be one appropriate to the sentence type, like disjunction or conditional probability. We also have a secondary disjunction rule here. So if the disjuncts are mutually exclusive, and only in that condition, we can use the simple conjunction rule. That tells us that when the disjuncts are mutually exclusive, the probability of P or Q can just be given by the probability of P plus the probability of Q. Again, I'll emphasize the generalized disjunction rule will work for any disjunction. The simple disjunction rule will work only when P and Q are mutually exclusive. We can also ask the probability of a negation like not P. So that's written as PR of not P. A question that would ask for the probability of a negation should include some sort of negation word like not. Like, what's the probability of not drawing a face card from a standard deck of 52 cards? The rule that will always work to give us the probability of a negation is, no surprise, it's the negation rule. And it's pretty simple. It's the probability of not P equals 1 minus the probability of P. Where does this come from? Well, we know that the probability of P and not P are two mutually exclusive statements. And they're also exhaustive. They're the only two options. You either have to be in circumstances where P is true or circumstances where not P is true. When you have two mutually exclusive and exhaustive statements, you have to be in one or the other. That means you can add their probabilities, and since they're exhaustive, they add to 1. So the negation rule can be derived from our simple disjunction rule. Sometimes we want to know the probability of a conjunction. That would be written PR of P and Q. And here we should see some kind of conjunction term in the written English. Normally that's going to be and, but it might be but or while or in addition, those kinds of terms that we should be familiar with. We might see a question like, what's the probability of rolling a 6 and then rolling a 5? To calculate the probability of a conjunction, the generalized conjunction rule will always work, just like the generalized disjunction rule will always work to calculate the probability of a disjunction. So the generalized conjunction rule tells us that the probability of the sentence P and Q, that conjunction, we can get the value of that complex probability by multiplying the probability of P given Q times the probability of Q. When you use this formula, what's important is to make sure you uniformly replace P and Q to the relevant sentences in your problem. So you have to pay some attention to the order. P and Q, that can be either direction because the order of the statements in a conjunction doesn't matter. But that means that the probability of P and Q either has to be the probability of P given Q times the probability of Q, or the probability of Q given P times the probability of P. So pay attention to the order in the right-hand side. And for conditional probabilities, we'll look at them a little more in a minute. We also have a formula that works to calculate the probability of conjunction in special circumstances, just like we did for disjunction. So if the conjuncts P and Q are independent, we can use our simple conjunction rule. That tells us that the probability of the conjunction P and Q can be given from the probability of P times the probability of Q. Again, that only works if we know that P and Q are independent. We also learned how to calculate the probabilities of sentences with some special properties that are familiar from our study of deductive logic. So if P is a tautology, then the probability of P is 1. That's because 1, that value represents certainty. It's certain to be true. That's what a tautology means. If P is a contradiction, then we know that the probability of P is 0. If something has a probability 0, that tells us it's certain to be false. And we can know that if two sentences, P and Q, are equivalent, then they have to have the same probabilities. Just like we would before, we can use a truth table to determine if some sentence, P, Q, or whatever it is, if it has one of these properties. And then, once we determine that it has the property, we can use these rules for what the probability is. We can also combine these properties with other formulas. For example, the probability of the conjunction of some sentence P with a tautology, that turns out to just be the probability of P. So far, we've looked at the rules for calculating the probabilities of sentences that are familiar from our study of propositional truth functional logic. Conditional probability, though, is unique to the probability calculus. We need to calculate probabilities of the form the probability of P given Q. We need to do that when we're asking questions like, what is the probability that a storm will develop given the current atmospheric pressure? Sometimes conditional probabilities will be given to us directly, but other times we need to calculate them. One way to calculate a conditional probability is using this definition. The definition is given by a formula. It just tells us that the probability of P given Q is equal to the following ratio. The probability of the conjunction of P and Q over the probability of Q. And we can use this formula as long as the probability of Q is greater than 0. With that ratio, we get a numeric value for the probability of P given Q. As I mentioned briefly before, we can combine the formulas from these various rules. And that allows us to calculate the probabilities of sentences that combine logical connectives. We just have to pay attention to the scope of our connectives if we want to calculate the probabilities correctly. For example, we might ask, what's the probability of the negation of P and Q? We see that written 3 lines down there as probability scoped over the negation of P and Q. To figure out how to calculate that, and what values we would need to know, we need to do some manipulation of our formulas. So we have to start with our wider scope connective, and that tells us we need to first determine the probability of a negation. The probability of a negation is 1 minus the probability of the sentence without the negation. That's what our negation rule tells us. So the probability of not P and Q equals 1 minus the probability of P and Q. But we're not done yet. We need to next determine the probability of P and Q. How do we calculate the probability of that complex sentence? Well, we're not told here whether P and Q are independent, so we need to use our general conjunction rule. That tells us that the probability of P and Q can be given by the probability of P given Q times the probability of Q. So we can substitute the right-hand side in this second formula into PR, P, and Q in our first formula. And combining that tells us that the probability of this complex sentence with 2 connectives is 1 minus the probability of P given Q times the probability of Q. We've looked at the core formulas of the probability calculus already, but we're now going to use 3 more useful formulas that we've studied so far and look at when to use them. We talked already about the fact that we can only use the simple conjunction rule when we know for a fact that sentences are independent. If we know that sentences are independent, that's going to come from what we know about facts about the world. For example, we know that the first dice roll, if we roll a die twice in a row, the first one doesn't impact the second. But we don't always know whether two sentences are independent. In that case, we can learn whether probabilities are independent by using the following test. Ignoring the cases where the probabilities are 0, we know that P and Q are independent if the probability of P given Q is equal to the probability of P. So in that case only, that's a way of telling us P and Q are independent. If these two probabilities don't have the same value, then the sentences are dependent. And again, if we don't automatically know the conditional probability of P given Q, we can calculate it because we have a conditional probability definition. We also looked at the law of total probability. This is a formula that we need to use when we want to determine the overall probability of some statement from its probability in two or more mutually exclusive and exhaustive conditions. Normally, we characterize the law of total probability in terms of mutually exclusive and exhaustive conditions that are a statement Q and its negation. But it could be any two or more sentences that form a partition that are mutually exclusive and exhaustive. So the general statement of the law of total probability tells us that for two sentences P and Q, we can calculate the probability of P by considering its probability when Q is true and its probability when Q is not true. In terms of a formula, that tells us that the probability of P equals the probability of P and Q plus the probability of P and not Q. This is the formula that most easily helps us see what the law means. But to get the most useful version of the law of total probability, the best formula for calculations, we have to do some substitution using formulas we've learned before. We substitute in to tell us how to calculate the probabilities of each of those conjunctions on either side of the plus sign. And since those are the probabilities of conjunctions, we have to use the general conjunction rule to tell us how to calculate them. So first, we need the formula for calculating P and Q. Then we need the formula for calculating the probability of P and not Q. And we substitute those into the conjunctions in the equation above to get the more complex but more useful version of the law of total probability, which is given in that formula at the bottom. The probability of P equals the probability of P given Q times the probability of Q plus the probability of P given not Q times the probability of not Q. And finally, we'll look at Bayes' theorem. The definition of conditional probability was one way we've looked at for how to calculate the value of a conditional probability. But we can also calculate the value of a conditional probability by using Bayes' theorem. What's special about Bayes' theorem is that it allows us to calculate one conditional probability by relying on its converse. So that means if we know the probability of Q given P and a couple of other probabilities, we can calculate the converse, P given Q. So we can see that in the simple form of Bayes' theorem. The probability of P given Q, that's what we're trying to calculate. We can get that if we know the probability of Q given P, and then we multiply that times the probability of P and divide it by the probability of Q. Now, of course, the simple form of Bayes' theorem is often less useful because we may not know the probability of Q. But we have a way of calculating the probability of Q if we know the probability of P and the conditional probability of Q given P, which we already know. Then we only need to know one extra value, the probability of Q given not P. So the more useful version of Bayes' theorem comes from the law of total probability substituting in for the denominator. That substitution gives us the formula, the probability of P given Q equals the probability of Q given P, again we have that converse there, times the probability of P, a relatively simple numerator. And then in the denominator, we have to add two probabilities. The first term of the addition is just the numerator again. So on the bottom we have the probability of Q given P times the probability of P. And then we add the probability of Q given not P times the probability of not P. That complex formula allows us to calculate a conditional probability, again, when we know the converse and some other useful values. Hopefully, this review has helped you better understand how and when to use the rules of the probability calculus that we've covered.